Hello everyone, my name is Li Kai from Nanjing University. Thanks for watching this presentation and being interested in this research. In this presentation, I will show you two parametric models based on the saturated and additive function generation principle. The purpose of the development of these two models is to facilitate architects to carry out performance-based design optimization in the building massing design. Let's talk about the background of this research. In the past decade, there are more and more researchers and architects argue that the performance-based design optimization can be an efficient way to help architects to explore many design alternatives. The exploration can help architects free from the design fixation and achieve performance-informed design process. However, there are still many challenges and difficulties for the architects to carry out such performance-based design exploration. And as a key factor in the performance-based design optimization, the parametric model is one of the major issues that prevent many architects to use the performance-based design exploration in their design. So in this research, we identified two challenges related to the parametric modeling and parametric model. Firstly, the parametric modeling is technically demanding and time-consuming for most practitioners. And secondly, they usually have a strong geometry and logical dependency in the parametric model. So the parametric model only generates design variant without significant design variability and differentiation. As a result, the design variant outputted by the optimization process is usually very predictable and not very informing. In order to increase the design variability and the differentiation among the design variant generated by the parametric model, there are usually two approaches that have been used in the previous study. The first approach is called combinatory model, which combine multiple generative algorithm in one parametric model. And the second one is called a voxel model, which represents the building massing design with many smaller voxel or massing units. However, these two approaches still have some limitation and weakness. So it will bring some difficulty for the performance-based design optimization process to identify feasible and high-performing solutions. So in this research, we propose another way to carry out the parametric modeling to overcome the weakness mentioned above. We use the saturated and additive function generation principles for the parametric modeling. The reason why we use these two principles is that these two principles can describe basically all the building massing design in reality, and it also have a tight connection to many passive design strategies such as courtyard atrium, self-shading, and the building massing with a solar envelope. So if we can use these two principles to as the basis for the parametric modeling, so the parametric model can reversely generate all the design variants that can be described by these two principles. So it means that we can provide a very large design space for the optimization process to search for the more site-specific and task-specific solution for solving the design problem. In terms of the implementation of the algorithm, I won't go into the detail of all the operators we use in the implementation of the algorithm. I will show you two key points when we realize these two algorithms. The first key operators is the Boolean difference and Boolean union. We use these two operators respectively in the saturated algorithm and the additive algorithm. And the second very important operator is alignment. The alignment is not only ensure that the desired variance generated by the algorithm can have a proper and reasonable geometry order, it also can enhance the typological variability. It is because the alignment actually will merge two smaller elements into one large one, which change the typological configuration of the design variant. So it means that even with the same number of the matching elements, the algorithm can still generate design variant with different typological variability. In order to demonstrate the advantage of using these two algorithms, we will analyze the feature of these two algorithms from the perspective of design space. So if we use the simple parametric model or combinatorial parametric model, the design space is usually separate and confined, which means that each design space usually contains one type or a limited number of types of building, such as the courtyard building or the building with a feature of solar envelope. So it means that the design optimization process can only search for the solution within this type of building. But if we use the subtractive and additive algorithm, these two algorithms can actually generate all different types of the buildings. So it means that these two algorithms is actually implicitly merge and integrate all the smaller design space into a large unified design space. The large and unified design space is important to achieve a valuable and meaningful performance-based design optimization. It is because that if we use a separate and confined design space, they will have two problems. The first problem is that in some cases, the design space may not contain the optimal solution for solving the design problem. And the second problem is that if the designers want to explore the design space, they have to construct many different parametric models, which is time consuming. So if the designer can have a large and unified design space, the design space can, on the one hand, contain maybe many optimal solution for the design problem. And the second one is that if the designer can use some technique to extract many of these optimal solution, it means that the optimization result can contain different design alternative, which can provide more information to the architect about the design problem. So in order to demonstrate the advantage and this usefulness of these two algorithms in the building meshing design, I will show you two case studies. The first case study is a slab-tile high-rise building. We set up two optimization objectives, which are the passive solar utility and the daylighting. We respectively run the optimization process based on the subtractive and the additive generated algorithm. And for the optimization result aimed at the passive solar utility, we can find that this design variant shows that the designer can use strategies such as the overhang structure to achieve cell shading or narrow the westward facade to reduce the solar irradiation received in the summer. So these two strategies can help to prevent the building from the overheating. And for the optimization result aimed at the daylighting performance, we can find that the optimization result indicate that the designer can elevate the overall building meshing, which can help to escape the shadow casted by the surrounding building or increase the indoor space, have a better accessibility to the nature daylight. For the second case study, we use the same optimization objective for the optimization, and so the information and the strategy reflected by this design variant is consistent to the previous one. But in this case study, we changed the building type from a high-rise building to a middle-rise deep-plan building. This case study can show that this algorithm can be used in different types of the building meshing design project, which so it have an advantage that these two algorithms have a very high reusability, which means that they can facilitate architects to carry out the performance-based design optimization without the parametric modeling. To summarize this research, on the one hand, these two algorithms can be viewed as the meta model of the subtractive and additive function generation principle. So it can be think these two algorithms as abstraction of the two generic building design principle. So in contrast, the most parametric model can be viewed as a and abstraction of a specific design object or the design task, which means that the ordinary parametric model usually embedded many task-related intention. So for these two algorithms, since there is no task-related intention in the in this algorithm, so it gives these two algorithms very high reusability. So the designer can use these two algorithms in different building massing design projects. And the second one, the second advantage is that these two algorithms can generate building massing design with very high design variability and differentiation, which can help the optimization process to identify more site-specific and task-specific solution for the different in different design condition and the optimization objective. So this is the end of this presentation. Thanks for watching. Here is some related paper to this presentation. Thanks.